Okay, in this module, I'm going to give a little bit of a background and an introduction to operations research. The purpose of this module is to provide a basic understanding of the development, formulation, and analysis operations research, or we often refer to as OR models, in addition to a basic background and history of operations research will be provided. So, one of the things that I often say about operations research is I feel that it is one of the least descriptive titles of a course that you can have. Now, I know that there are cases where maybe, there are other courses where you look at the title and it actually is or less descriptive. But operations research is the kind of course that just by looking at the title, you don't really gain an understanding of what it is. So if you think about a class like, say, circuit analysis or fluid power, dynamics, courses like that, while you may not know anything about the particular topic, anything about the details, psychology, history, literature, you kind of understand maybe what the course would be about, maybe what a few topics would be about. But the average person, if you ask them to name one topic within the context of operations research, they probably couldn't name anything. So operations research, it's often known as management science. So sometimes you'll see these courses being taught in a business school, a business program, and a lot of times these courses will actually be referred to as management science. It's basically a scientific approach to decision making that seeks to best design and operate a system, usually under conditions requiring the allocation of scarce resources. So if your resources aren't scarce, then usually it's pretty easy to work within a system. If you have all the equipment you need, if you have all the resources you need, if you have all the time you need, all the people, that sort of thing, it's usually not that big of a deal. When we look at system, we mean an organization of interdependent components that work together to accomplish the goal of the system. So, for example, Ford Motor Company is a system whose goal consists of maximizing the profit that can be earned by producing quality vehicles. So, Ford Motor Company would be a perfect example of where you would use operations research. Imagine everything it takes to build a vehicle. Just say in the production line itself. Don't even imagine having to go to, get the ore out of the ground to actually smelt the iron or the aluminum or whatever materials you're using. Let's just suppose that you're buying all of that material from a vendor and you're bringing that into a production line. What's the best way to do that? How much do you need of each product that you're using in the manufacture of the vehicle? What people work? Where do they work? The throughput on the assembly line. So that really is what operations research has to deal with, that sort of thing. So where did operations research come from? Well, operations research is a relatively new field. It was actually coined during World War II when British military leaders asked scientists and engineers to analyze several military problems, such as the deployment of radar and the management of convoy bombing, anti-submarine, and mining operations. So if you've ever in your life heard the phrase, you get the biggest bang for your buck, that is directly coming from operations research, and that phrase actually came out of World War II. So as unfortunate as it may sound, that was really what these scientists and mathematicians were asked to do. They were asked to basically get the biggest bang for their buck. So during that war, the United States and the Allied forces had a limited number of resources. It's not like now. If the United States were to go to war, we've been doing OR for the past 75, 80, 90 years. We have probably plenty of stockpiles of weapons and bombs and guns and planes and tanks and that sort of thing. So that would be more logistical of just how to move them around. But you have to realize during World War II, we weren't really prepared to go into war. Our military had been somewhat dismantled after World War One, and we were in times of peace. So starting that required more resources than we had. Especially if you look at Britain, they were actually in the war on the front line being bombed. So so they had to figure out how they were going to allocate their resources in a maximal manner. And operations research actually helped out tremendously with that. So you've got limited number of bombs. Where do you place them? You have a limited number of radar stations. Where do you place them? And these were the problems that they were actually dealing with. In modern times, operations research, that's a whole field in of itself. It's actually called military operations research, and it has to do mostly with logistics of how do you get things from where they are to where they need to be. And that is not really a trivial task if you think about it. Supplying food and ammunition, fuel, people, that sort of thing. That's a hard problem. So what they're looking at trying to do is do it in an optimal or near optimal manner. But because of the war effort, there was an urgent need to allocate scarce resources to various military operations and the activities within each operation in an effective manner. But when the war ended, it was all said and done, now this, I'll call it, skill set had been developed during the war effort, and there was experience, techniques that had been developed, and these techniques were then brought into private industry. So when the war ended, the success of OR and the war effort spurred interest in applying OR outside the military as well. So after World War II, there was this industrial boom, basically because the rest of the world was in ruins, or I should say the developed world was in ruins, and the United States was one of the few countries left that hadn't been really directly affected by the war. When I mean directly affected, essentially there had been no damage on American soil. From from the opposing forces. You might argue, an incident or two or something like Pearl Harbor, but that actually happened before the war. But you know what I mean. Our cities hadn't been bombed, and roadways hadn't been torn up, and infrastructure, power plants and things like that hadn't been destroyed. So the United States was really riding the wave during that period of time. So as the industrial boom following the war was running its course, the problems caused by the increasing complexity and specialization in organizations were again coming to the forefront. And so the techniques that were developed out of necessity now could be applied to the business world. So essentially these analysts started looking, well, how can we go in and make our existing factories or any new factories that we build, how can we go in and optimize them and make them more productive? And hence started the field of operations research. So when we look at OR applications, below are some examples of applications in which operations research is used. Includes critical path analysis or project planning within a project management network, design the layout of a factory for efficient flow of materials. So that's a classic OR problem. You have a factory that you're designing either from the ground up or that you're going in and maybe redesigning. Construction of a telecommunication network at a low cost while guaranteeing quality of service. I once heard a statistic, and the older I get, the more these statistics elude me, but it was about building cell phone towers. And back when these cell phone towers were first being built, essentially they were placed in pretty much, I'm not going to say random or haphazard locations, but they were placed in a non-optimal manner. And now if we could go back and redesign that network from the ground up, like assume that there had never been a cell phone tower built, and you could go in and design them and put them where they needed to be from day one, it was something like we would need like 10 times fewer cell phone towers, simply because they would be placed in an optimal manner instead of just kind of willy-nilly, well, we've got a bunch of people that live here, let's put one here, we'll put one down the road, put one here and there. But that was a field that kind of emerged over time, and it just happened to be the way it is. But in modern times, we understand this, or we should understand it, that if you're doing something from the very beginning, you have an opportunity to go in and do it right with these modern techniques. Road traffic management, one-way street allocations, determining the routes of school buses, or UPS trucks, things like that, designing the layout of a computer chip to reduce manufacturing time. So you look at this bottom two, designing the routes of a school bus or UPS or that sort of thing, versus designing the layout of a computer chip. Those may seem like those would be completely different problems, but it turns out that the two are nearly identical to one another. It just has to do with a matter of scale, that obviously one is much larger, but when you think about it, you're essentially doing the same thing. When you're designing the layout of a computer chip, and you have to go in and these automated machines actually go in and stamp them out, put transistors in, diodes, whatever it may be. What is the best way of doing that? I mean, think about it. There's an optimal way of doing it, and there's a non-optimal way of doing it. Now, the optimal way, the absolute best solutions, many times, is they're very difficult to find, but we usually can find really good solutions, which are, I'll say, good enough. Managing the flow of raw materials, efficient messaging and customer response tactics, uh, robot or automating human-driven operations processes, and the list goes on and on and on. An example of a using OR is the airline industry. That's a perfect example. If you think about all the flights that take off and land in a given day, and who has to be on those flights, how many hours a pilot can fly, how many hours a flight attendant can fly, where the planes should go, where they should land, how much fuel they should get, the scheduling. That is a classic operations research problem. Another classic operations research problem that I often go over, just is I'll ask you now to go in and let's take a company like let's just take a company like Walmart. Okay, I want you to think about the layout of a typical Walmart. Now I know that, let's say this is the front. I know that different Walmarts are laid out differently. That in some ways is done intentionally. So if you go to one Walmart, you know where everything is. If you go to another one, it may be completely reversed or moved around. So you can't really use that existing knowledge to help you find something. But here's what I want you to do. I want you to think just for a moment about in any typical visit when you go into Walmart. And I don't mean a visit where you specifically decide today you're going to go in and buy a 70-inch, flat screen television. I mean, on just an average trip, what are the top 5 items that you would buy? Now, you may buy more than 5. I'm just saying on an average trip, in your mind, just get out a piece of paper and just start writing down what those items would be. Take about 10 seconds and just think, what top 5 items on average would I go into Walmart and buy? Give you a minute to do that, and then I'm going to start just listing some items that I feel would be items that I would buy. Number one on the milk is, or another one on the top of the list is milk. Okay, especially if you have kids, you got to go in and get a gallon of milk. Then you've always got bread. Got to get some bread. All right, milk and bread. Those two are the big ones. Let's see, what else do you need? Maybe some toiletries. How do you spell that? Toiletries. Toothpaste, shaving cream, something like that. What else would you get? Um, well, when I think about, going at some point, you may need light bulbs, you may need extension cords, you may need um, just kind of on that side of the store, um, some piece of hardware, windshield wiper fluid, something like that. So I'm just going to say maybe hardware. And hardware could be, like I said, a light bulb, something like that. Um, I don't know, windshield wiper fluid, something like that. And, for the kids, maybe you buy some socks. I don't know. I'm not a female, but I am married, so maybe, something like pantyhose, pajamas, just something, you know. Um, some people in the past have said diapers. So maybe I'll put something like 6 down here. I know I said 5, uh, but diapers. And then if you buy diapers, then immediately you're going to have to buy some beer. Okay. The reason why I bring that up is actually these two, through a data mining exercise that I think was conducted by Walmart, just actually at looking what people buy, it was found that there's a correlation between diapers and beer, and it has to do with men. That if a man is sent to the store to buy diapers for the baby, that he feels entitled that he needs to get him a case of beer to kind of reward himself for being inconvenienced. Now I don't know if it's that extreme or not, but it turns out, and we're going to talk about this throughout the course, a little bit of data mining, what data mining actually is. And if you just kind of want to know now, just go to Google or Wikipedia and type in data mining. But what data mining does is it looks for these previously unknown correlations that exist in a system, something that a human being would probably never pick up. Because it's just far too complex, too many items you're trying to analyze, and these data mining algorithms will actually pick them up. So let's go back. All right, so milk, number one. So if you just have to go into a store and buy one item, what's it going to be? It's going to be milk. Okay, so where is milk located? Well, I'm going to say milk is going to be located here. It could be on the other side of the store, but just think about a Walmart. It's going to be located all the way in the far back corner. Okay, so let's suppose that you're buying these in order, which wouldn't necessarily be the case. Okay, I get you could move them around and buy them in another way, but it really wouldn't matter if you think about it. So you're coming into the store, you come down here, you go all the way down, you get your milk, and then where do you go? You go up here and you get your bread. Okay, so you've got two of them, milk, bread. Now you've got to get some toiletries. So you go all the way across the store, okay, over here, and you get let's suppose you get your toothpaste. Okay, now then you decide that you're going to go down to right here, and you're going to get yourself a light bulb. All right, and maybe as you stop by here, you get some windshield wiper fluid. Windshield. Okay, then you come back across. Now, as you're coming back across, even though you're not intending on buying this, you've got your kids with you, and what are they going to want to do? They're going to want to stop here and look at the toys. All right, so that's going to cost you $20 to pick up a extra Lego or something that you weren't intending. Then you finally make your way out of here. Then now you're coming by, and here's all your electronics. Okay, so you know what? You've had a rough day. You've got 3 kids fighting, screaming. You come in to get some milk, some bread. You come over to get some toothpaste. Time you get to the toys, they're ready to go home, and you feel like you need to reward yourself. So you go ahead and pick yourself up a 70-inch TV. Forget the TV. You go pick up a $2.99 special DVD of some movie that you haven't seen, some maybe inspirational movie because you're feeling down. It's only $3. You might as well go ahead and pick it up. You make your way over here, go down to the center of the store, you pick up your socks or your pajamas or your pantyhose or whatever it is, and then you go on, make your way out, and then decide to go over here and go down one of the aisle. Now they've got you some Pepsi. They've got all kinds of you know, candy, chewing gum. All the kids want the pack of chewing gum. You need some lighters. You didn't know you needed some lighters or some lipstick, or not lipstick, but maybe chapstick, what of that sort of thing. And then you come on up, decide, well, I'm gonna go out the door I came in. All right. So what just happened? What happened was you just traversed the entire store, or nearly the whole store. So you went in there planning on spending $35. Okay? Some bread, some milk, some toothpaste, a thing of light bulbs, get you some socks, pajamas, pantyhose, and yeah, kids could probably make it another week. They have enough diapers. $35, and you come out and you just spent $250. That is an OR problem that Walmart has spent years analyzing the buying habits of people, and they lay out their store accordingly. So your goal is to go in as you would see it if you kind of thought about what operations research should be doing for the customer. Your goal is, well, you should put all of these items maybe together. Just put them at the front of the store. Um, and that's why you have convenience stores that sell things for about twice what you can go to Walmart to buy them, because you're paying for the convenience. Walmart doesn't want this to happen. They want you to spend as much time in the store as possible, and then you're going to spend as much money as possible. So it's almost like an operations research problem in reverse. I mean, even though it's not, this, all you have to do is just say, instead of minimizing something, you're trying to maximize something. So if you look at it from a point of view of, say, UPS, and they have 20 packages that are located all these different different addresses. I don't know if I've got 20 or not. I'm just trying to create some random places. And you want to move around, you're not going to do something like this. That's not what you're going to do at all from a UPS point of view. From a Walmart point of view, that's what you've tried to get your customer to do. From a UPS point of view of actually delivering these packages as efficiently and timely as possible, and minimizing, say, how much fuel you use, you're going to try to do something like this. Now, I don't know if this is the best path, but that's what you're going to try to do. You're going to try to actually minimize that route to save money. So then the question becomes, what is your objective? What are you trying to do? Are you trying to minimize, or are you trying to maximize something? So that's a classic example of operations research. And like I said, the list just goes on and on and on with OR topics. Okay. So solving problems using operations research approach closely resembles the scientific method of problem solving. So if you remember, the scientific method consists of the following steps. One, remember you learned this probably in 6th grade, observe the system, develop a hypothesis, test the hypothesis with an experiment, draw a conclusion, and then report your results. Well, you do something very similar with the OR modeling approach. The first thing you do is define the problem, then you formulate a mathematical model, you develop a computer-based procedure, you test the model, and then you implement the model. So here are kind of the steps that that you would go through, kind of like a flow chart, and we'll come back to that here in just a minute. Okay, so when you actually look at each one of these steps, I just kind of went through them quickly, we're going to talk about them in more detail now, is the first one, define the problem, or problem definition cannot be understated. I just see this, I've seen this so much in my life. of people, the inability of people to actually determine what the problem is. And believe it or not, that is, I think, one of the most important steps, and not just operations research, but in any problem that you have in life. Even at the personal level, you see people that they have different problems, and we all have problems. It's not being critical of anyone, but you'll see them say, "Oh, I need to do something like this, or I need to do something like that, or the problem is this, or the problem is that." And you think to yourself, "No, that's not the problem. That's not the problem at all." So if you can't properly identify what the real problem is, then there's no hope of solving it. So perhaps the least discussed and most important issue pertaining to operations research is defining the problem. So without a proper problem definition, there's little hope in accomplishing the true objective of the researcher. So defining the wrong problem can easily result in one, no solution being found, or the wrong solution being found. So it's actually the right solution, but it's to the wrong problem, or an inappropriate solution being found. So a stated objective or mission statement often helps to focus attention on what the problem actually is. Um, it's just good to have what it is you're trying to do. And a lot of times that's why you have a stated objection, or not objection, objective, or a mission statement. And if you can get a group to agree on what the actual mission is, what it is you're trying to accomplish, then a lot of times if you're having to work as part of a group, you can keep people on task. Because if you've ever been in a meeting with a group of people, a lot of times it just turns into a free-for-all. The next thing you know, you get to talking about things that aren't even relevant to the company, the job, anything. It just takes off in a direction. So it's all right, people. Stay on task, and this is what we're trying to accomplish. And the first thing you need to do is get buy-in from the people working with you, above you or below you, or whoever it may be. Of, is this what we are actually trying to do? What is our objective? I was in a meeting, and I know this can be dated, because you may be listening to this at some point in time that isn't my today. But just here recently, I was in a meeting, and it won't change. So if I'm if you're watching this video 2 years from now, I guarantee you it won't change. The story I'm about to tell will be just as current as it is at this moment in time to me. But was recently in a meeting, and the group was proposing to do something, and on about 5 different occasions, I would pause, say, "Excuse me, can I say something?" And I would say, "But what is your objective? What is it that you are trying to do? What are you trying to accomplish?" And then, you would get some answer. And I would say, "The problem is doing what you or say you're going to be doing, getting this committee together, whatever, is not going to accomplish this objective. Uh, you're actually going to accomplish the opposite of what you're trying to accomplish, because what you're trying to accomplish is to make something simpler and more streamlined. And when you bring in 10 people and form a committee, what they're going to do in the process of trying to simplify this is make it more complicated." And then, "Oh yeah," and then he'd come back, and then finally you just say, "Okay, all right, well, have fun. Let me know how that works out." And that's just the way you also have to accept that of life. Okay, so problem definition. Uh, just don't underestimate how important this is. It's not just some 5 minutes I've spent talking about it because I don't have anything better to do. You have to figure out what it is you are actually trying to accomplish, especially in the context of OR, because when you start applying these techniques, if you apply them to the wrong problem, you're not going to get the right answer. I guarantee it. So, model building. An OR model is simply an abstraction of a real problem. Models vary from flowcharts, procedures, to charts and graphs. However, in the context of OR, a model has a very specific definition. It is a mathematical relationship. It consists of one, an objective function. What are you trying to accomplish? What is your objective? And in a classical OR model, an objective function is an equation usually, okay? That it's not just, oh, this is what we're trying to accomplish. It is composed of decision variables, which I'll talk about here on number 3. It has a set of constraints. So any real world problem has constraints. So how much time do we have? How much money do we have? Maybe how much equipment do we have? Human resources do we have? And that sort of thing. So this is what makes problems hard, having constraints. So you have to identify your constraints. And then you have to determine what your decision variables are. So your decision variables may be, how many products of X are you trying to produce today? So if you look at a problem like, we're trying to maximize our revenue. Okay, well that's a good objective. Maximize revenue. Okay, what is revenue? Well, revenue, well, it's money. Okay, it is. But what does revenue, what does it consist of in the context of your industry or your company or within your system? Well, revenue is how many widgets we sell of A, how many of B, how many of C, how many of D. Okay, fine. Now you have 4 decision variables, A, B, C, and D. So you're trying to maximize how many you can produce, not just how many you can produce. If one brings in more revenue than another, you may decide to produce more of one than of another. So those are your decision variables. So as an example, consider a business that sells a product. Suppose that the product costs $10 to manufacture and it sells for $30. So the model that determines the profit is simple. A lot of times in operations research, we denote the objective function is Z. It's just a standard. Why? I don't know. But just about all models, you say Z equals something, and Z is known to be your objective function. So Z will simply equal 30 times X minus 10 times X, or 20X. But this very simple model defines your profit because you're selling the products for 30 and it costs you 10 to make, so you're making $20 per item. Okay? So in this equation, X represents the number of units that the number of units of the products that are sold, and Z represents the total profit that results from the sale of the product itself. So the symbols X and Z are referred to as variables. In the context of OR, like I said, the Z is commonly used to denote objectives such as profit, revenue, cost, etc., whereas the symbol X is used to denote decision variables. And so when you have 2 or more decision variables that are used, they're denoted using subscripts such as X1, X2, X3, all the way to Xn. Z is a dependent variable because its value is dependent upon the values of X, whereas X is an independent variable because its value is not dependent on anything else in the model. It is what it is. Okay. Now it may be constrained, but it's not dependent, and there's a big difference. So I can say, well, X is how many widgets I'm going to make in a given day, but it takes 10 minutes to make each widget. So that means in an 8-hour shift, I can make 6 an hour, 8 hours. I can make 48 a day. So X may be constrained, but it is not dependent on anything else. So suppose that the number of products that a company is able to produce depends on some other resource such as raw material or labor. So for example, suppose each product requires 6 kilograms of aluminum to manufacture. However, there are only 150 kilograms available each day. This statement implies the use of a constant. The limiting factor for all the profit of a given day is the amount of aluminum available, assuming that all products manufactured can be sold. So suppose we want to maximize the profit for this company. The model that describes the system is going to be, we want to maximize Z. Z is equal to 20X, okay? Because we're going to assume that this is the same product, so we can make $20 per item. Okay, so Z is going to be equal to 20X, subject to 6X equal to 150. This is the total amount of aluminum, and this is the amount of aluminum we have for each product. So if we have two products that we're making, it's going to be 12, 3, 18, and so on. So the values of 20, 6, and 150 are what's known as parameters of the model. These parameters may be fixed or they may change over time. And we'll look throughout the course at models that kind of explore both types. So solving this model is very straightforward. First, we need to determine how many products can be produced based on the amount of aluminum available. So that's going to be 6x equals 150, x equals 150 divided by 6, so x is going to be 25 units. Substituting the value of 25 for x into the profit gives us 20 times 25, or $500. So what this means is that we can make $500 off of this endeavor. This is a very, very simple, very straightforward problem, but it gives you some ideas of objective functions, constraints, and decision variables. So problems such as these are relatively easy to formulate and solve using algebraic methods. However, most real-world problems are vastly more complex and you can't easily solve them by hand. So computers are often implemented to solve more difficult and complex problems. So an example of how this problem can be formulated and solved using OpenOffice, also known as LibreOffice, or what we're going to be using in this class is Excel. But I'm going to give an example of how to do it in OpenOffice, and then I will give more examples throughout the course using Excel. When I first started writing the book that you're reading, I wrote the majority of that myself. I was trying to find some free software so students wouldn't have to buy, the software, and not everyone had access to Microsoft Office. Now the world has changed. Companies like Google came along, created Google Docs, offered it for free, and companies like Microsoft had to change their business model. And one of the ways they changed their business model is now getting a hold of Microsoft Office is pretty easy to do, especially if you're a student. You can get free versions of it. The world changed, so we're going to be using Excel for this course. It's actually a little more powerful. And what it will do, I shouldn't say more powerful, it's maybe a little bit easier, maybe I'm just used to it, we'll just say that, compared to OpenOffice. So basically they're almost identical to one another. So if you know how to solve a problem in one, you know how to solve it in another one. So it's very simple. So here's like a spreadsheet you would see where we've got it laid out. We've got these labels here: manufacturing cost, selling price, raw material per unit, total amount of raw material. So our manufacturing cost, we're going to say 10, selling price is 20, raw material per unit is 6, total raw material is 150. So our profit is simply going to be 20 times B9, because 9 down here is going to be our decision variable, or our dependent variable, what can change. Our constraint is going to be 6 times B9. So whatever this value is, these cells will change accordingly. And then I'm going to go in and solve this, and I will show you how to do this in subsequent lectures. So this is more, I'm just presenting to you what it will look like. So if you don't understand this, don't panic. I will actually go through step by step and show you how to put this in the Excel spreadsheet, and how to bring up solver and the parameters and the dialog box and everything. Our target cell is going to be B6. B6 is simply what our profit is. It's this cell located here in blue. We want to maximize this value by changing cell B9, which is our decision variable, okay? And we have a limiting condition or constraints that B7 has to be less than or equal to 150. So B7, which is the amount that we are actually using, has to be less than 150. So I just hard coded it put 150, but I actually could have put in cell B4, and then this constraint could change if you needed it to. And then we solve it, and the answer we get is it says solving is successful. You get a result 500. You want to keep it, and you can see how it changed this decision variable to 25, and our profit is 500, and we actually used all of our raw material of 150. So it's pretty simple. So as with all systems, an OR model must be tested to ensure it is correct and giving valid results. So the purpose of testing an improvement of a model is usually referred to as model validation. Model validation is difficult to describe because the process depends on the nature of the problem being considered. So it's hard to just for me to go in and tell you how to validate a model. It really depends on what kind of model you're trying to validate. Okay, so there's courses that you can take in that, verification and validation of models, but that's what it's referred to as, validating the model. So large models can present an especially difficult task of model validation because of the large number of decision variables and causal relationships. Mistakes can be easily made. Therefore, the model must be thoroughly tested to try and identify and correct as many flaws as possible. Hopefully, after a number of iterations, the major flaws have been eliminated and the model can be reliably used. So, the final step of the OR model building process is implementation. If the results of the model are not used, then the whole modeling effort was useless. So the success of this phase greatly depends on the ability of the modelers to convey the usefulness of the results of the model itself. Therefore, many modelers find themselves playing the role of salesperson to decision makers. So what this means is you go in and you do all this work, but now you have to get this implemented. You have to get buy-in from your superiors of actually making a change to the process. So sometimes you have teams of people that do this because you may have someone that's really good implementing, building the model, solving. They're really good computers, but they're not really good at presenting. So you have to have someone that has softer skills that's able to go in and convince management that this is what we should actually doing. So it can be a difficult process, and a lot of times you'll find yourself frustrated because you actually understand the process at the ground level, and you understand everything that's going on, and you understand why you're proposing the answers you're proposing, because the model you built, these are the results that were obtained from that model, and then someone else just totally discounts it, and they don't really get it. And you can find that it can be very frustrating, so you have to keep that take that into account. So like I said, this is especially true when the results of the model suggest that a significant number of resources and capital are required to show improvement of the system. Because of this fact, it is often beneficial to have someone on the OR teams that convey the ideas and suggestions of the model results. It is also important to have the model clearly documented so that management can easily understand the purpose of the model and the results that the model yields. Another important step is to keep the decision makers in the loop during the modeling process. So if you keep them in the loop as you're building the model and as you're obtaining results, it's easier to actually convince them later on. So by keeping them updated and informed, the OR team makes them share stakeholders in the modeling process itself, and the recommendations are less likely to be rejected. So remember, if your recommendations are not accepted, then the entire modeling effort was useless. So just think about that for a moment. It's like multiplying something times zero. You go in and you do all this work, all this analysis, and if someone says no, you might as well not done any of the work at all. So this can't be understated either, that just because you know what you're doing and you can get results, it doesn't mean it's going to be implemented. So you have to think while you are developing these models, okay, what can I do to make sure this gets implemented? Because if it doesn't, then I've wasted my time. Okay, so as an overview, refer to any handouts. If available, refer to the optional reference chapter in the text. Be sure to complete the assigned homework and review the lecture presentation and notes pertaining to any questions that you may have about the material that we covered in this module.